students, basically the idea is that, you know, we will try to keep the time for the students. I think we've helped you with it. You know, I'm very good with it. And I'm very good with it. But you are very good with it. And basically, we're going to touch on issues that have to do sort of with object recognition and representation of objects. And then I'll move to, not me, Leah will present, the last speaker will present something about, which is related to the motion perception issue that we had talked about, or basically integration of information when the context changes. Okay, so something which has to do with prefrontal cortex, but still at the sort of context operation. And so I think we'll start immediately. Start, I think it's first. So please come along. And if there are any other questions for me, Stav is preparing to set up a talk about things that we talked about, which were unclear. That's the time for me to do this. The telephone, the right time? Can I check it?
Okay, for all the speakers, my phone will ring and make noise at 20?
Yeah, so
20 minutes.
Yeah, the plan is 20 minutes for each speaker, plus we have time for discussion, maybe 5 minutes. Well, a total of, 90 minutes. So, yeah, 5 to 10 minutes that we need for discussion. And I urge you, if something's unclear, well, depending on the speakers, you know, how they feel. But generally, we want to make sure that it doesn't really matter, I told the speakers, how much information is passed, as long as what is passed is clear. So I encourage you to ask questions just as I did in my talks, you know, and I think the speakers, okay, they're a bit tense, we will help them with that. You don't have to know everything, but it is important that we make this in a way which would be useful for all of us, not just for the speakers. Yeah, but how do you mean? כן, בסדר, בהצלחה, רק זה, אבל...
Warm or too cold for you?
כן, מה? אתה מורם? מה? אתה מורם לדבר בדבר, כי אני לא אשמע אותך. עכשיו פוינטר, כן. פוינטר, יש כמה שיטות, אפשר להשתמש בפוינטר שלי, אפשר להשתמש בפוינטר שהוא דרך התוכנה.
כולנו קוראים לו אחד, נושא שלי.
שירוק, ואז מה כבר שפותח מזה. זה פוינטר, עכשיו בואי נראה שהוא עולה על המסך. Looking good, בסדר? Okay, you're on.
Hi, I'll talk about Russell and Carl Center, and selectivity and tolerance both increase as visual information propagates from cortical area before.
I can't hear anything.
Exactly.
Oh my God.
In your case, it's absolutely, you know, with me, there's no problem, but with you, I think that we definitely want to sing it.
Hi, 1, 2.
Okay.
A.
Okay.
נגיד שאני לא בדיוק מותאם לדברים. אוקיי. נראה לי שזה בסדר. Do you hear me? Yes. Refreshing change. Okay. So I will talk about Russell and Carl's paper. Selectivity and tolerance both increase as visual information propagates from cortical area V4 to IT. And as you can guess from this title, what they wanted to do is to look at the ventral stream and to see how both selectivity and tolerance increase as you go along it. And they specifically look at V4 and IT as areas that represent different stages in the stream. So, yay. So let's talk about selectivity and tolerance. So selectivity is, for example, the ability to, for you, for example, to recognize that this is a chair and this is a shirt. And also, it's your ability to see that this is a chair and this is a sofa. So it's between categories and it's also within categories. And you'll probably agree that this is a very important feature you have in your object identification. Tolerance is your ability to generalize, whether it's over the angle, the size, the light conditions, and this is also very, very important for object identification, and the combination of them is the real magic that our brain does. So, okay, so specifically, in their experiment, they had two monkeys that were recorded while they watched a stream of pictures. One was just fixating on them, and the other did a task when he needed to identify a motorcycle. And okay, so more specifically, in this experiment, they wanted to compare V4 and IP, which is quite difficult because they're a little bit different from each other, right? Because as you can see, their receptive field size, for example, is in V4 is a lot smaller, and also it's arranged in different ways. But they didn't want to, unlike others, they didn't want to change the size of the picture and match it into the RF size. They decided to look at it as a population, because they wanted to see how these areas respond to the same picture as it is in real life. And this is just what the area they recorded from in V4. The blue thing is the recording chamber. So what did they do with this data? So as you know, we talked about it in class, each neuron is responsive in some way or another to pictures in these areas. And since they wanted to look at the population response, they actually represented it as a response vector. So this response vector is each element in this vector represents another neuron in the population. And what they did is that they counted the spikes in 200 milliseconds for each neuron, and this is how they created this vector. So this is an n-dimensional vector, and I mean, it is a vector in n-dimensional space. But if we want to simplify it a little bit, and we want to look at it as if it's just two-dimensional, so here we have neuron 1 and neuron 2, this vector is going to be a dot in this space. So why do we have these clouds? As you know, neurons are noisy, and they don't respond in the same way for two repetitions of the same picture. So each dot is one repetition of a picture. Each cloud is representing a different response to the same picture being repeated. So the thing they did with this data is that they used a linear classifier in order to find an optimal hyperplane to separate each cloud from the other cloud, each image from all the other images. So they took a part of the data, they trained the model on this part in order to find it, and then they tested it on another part of the data in order to see how many errors there are, and if it's a good model. So the first thing they wanted to test is selectivity. And for this they came up with this sensitivity to scrambling. So what they did to the stimuli was they took natural images and they applied a scrambling such that it extracts the local features from the natural image, and it arranges them randomly. So what happens is, you can see it very intuitively, I think. For example, here you can see the child, because this child is a result of the conjunction of all the local features. But when you scramble it, you don't see it anymore, and this is the difference between the scrambled images and the natural images.
So when you talk about local
mean, I think.
I can help. It's the output of V1 neurons, okay? So you have V1 neurons are tuned to orientation and specific spatial frequency, and as we talked, there's sort of an array of these covering all space in all frequencies and in all orientations, right? So you equate the scrambled images and the natural images are equated for the output of V1.
Yeah, yeah.
Okay?
Yeah, and this is also, you can see it also in their hypothesis. Yes.
They record one neuron at a time, or with the extracellular array electrode, or what's the recording method?
They had this recording chamber.
One at a time.
Yeah,
One
okay,
at a
sorry.
time.
It's one neuron at a time,
And
they
they're
show
taking
the whole picture arrays, and then they switch to another neuron, and so on.
And they're recording for how many? Like a few hundreds of neurons? What is N?
Yeah, I think so. It's yeah,
150 or
something like that.
Okay.
Okay, so the hypothesis behind this method was that in the earlier stages of the ventral stream, you have a representation, like what you just said, of the more of the local features. So if you look at the different natural images, they will be arranged in the space as separable clouds. But also when you scramble the images, since you have the same local features, they are still there. You get a slightly different representation of the clouds, but they are still separable. And as you go along this ventral pathway, it's not the performance for scrambled pictures is decreasing, and when you and you end up with just some collapse of all the clouds in a way that you can't distinguish between them anymore. So, okay.
Another question.
Yes.
Still not clear. So the comparison is between the natural and the scrambled. It's a pairwise comparison, or it's a Ross group comparison?
What do you mean? Again?
So you expect these clouds of the vector responses to be completely separable if you compare all the images on the left, all the different natural images, or is it a pairwise thing, comparison?
This is. I think they took each pair from the natural images and they measured the performance for each pair of the natural images and then for each pair of the scrambled images, and then they did this kind of comparison between.
Pairwise.
It's a pairwise comparison. For each natural image, there's scrambled pairs and matching image, right? Because these do not match in their sort of output in terms of V1 filter properties as well, right? These are not the same, okay, but these do match.
So it's always a pairwise comparison.
Always a pairwise comparison.
So, okay, so this was the hypothesis. So what you can see here is that this is the results for 140 neurons. So you can see really similarly to what you saw here, this relationship between this interaction between the graphs. You can see it also here. This is just an example of 140. This is for a varying number of neurons. And if they took 121 neurons in V4 and 140 in IT, which is the number of neurons where their performance is equal for natural images, it was even more convincing and similar to their hypothesis. So again, the conclusion from this is that according to this test of selectivity, IT had a better selectivity than V4.
Okay, how do they sort the neurons here? I mean, okay, you take...
Sort?
Yeah, you said here, I mean, the graph shows that as you increase the number of neurons, your performance gets better. But do they take just a random number, when they say, let's say you take 50 neurons, is this just a random choice from the 150?
Yeah, actually I don't remember.
I'm asking because I don't remember myself.
Okay. Okay.
I suppose so, because we see there's some standard deviation. So I think,
Yeah.
what does the standard deviation mean? Not bad, right? I mean, it's...
Afterwards, they look at specific neurons and sort, but I think in this part of the paper it's still random, they say.
So you can pick just a 50 out of the 150
Yeah.
randomly, and then you're going to get,
Okay, so we are
And
going
what is
to
the
this
leftover
activity.
graph? I mean, you didn't explain what's the difference between the lower
No,
and
actually I did, because I said that here they took different number of neurons for V4 and IT. And in this number they got equal performance on the natural images. And they showed it too, I think, because it looks pretty and really matches their hypothesis. They didn't say something further. Why you have okay. Yes.
What does it mean to be 70% correct? It's not completely clear.
What does it mean?
Let's say I take
If you
100 neurons, and I show this natural image stimulus. What does it mean to be 100% correct? If I give you 1 neuron, you can be 5% correct? Is it based on the neuronal information? Or is it based on some kind of... what does it
I'm
mean
not
to
sure I
be
understood
correct?
your question. I just think when you measure this kind of
too fast over this, so maybe he goes back to this one. How do you decide if it's correct or incorrect?
okay, so for example, after you train the data, you trained on one part of the data, you take another part of the data, and for example, you have a dot, which is a blue dot. It's supposed to be this image, okay? I mean, you know that it's image, but you see now the vector, okay? So if you get it here, you're good, but if you get it here, it means that it's an error. So this is how you measure it. Okay, so this was the activity. So the next thing they wanted to check is tolerance. And for this, they came up with this task. So as you can see, this is they call it a reference stimuli, which is a picture, for example, of a square on a gray background in the middle of the picture. And they took this reference and they did some transformations for it. So they increased the size, they changed the scale, they changed the position, and they put it on a natural background. And they wanted to see the generalization. Okay, so the idea was training the linear classifier on only the reference stimuli, and then checking it also on all the transformations. And the hypothesis was that in earlier stages, there is no such good generalization. So if you train it only on the reference, the other transformations are mixed with other images, and you can't really, I mean, this hyperplane doesn't reflect that it's the same object. But as you go along the pathway, the generalization goes up. And then when you only, also if you train it on the reference, if you want to check it afterwards in the test, after the training in the test, on the transformation, they end up being in the right side of the hyperplane. And you understand that it's the same object. So this was the hypothesis. And this is data that they show for position. So it looks like they showed it because it's the best looking, because, for example, the scale is not so convincing, but here you can see that it really matches their hypothesis. And another thing that to say for them that they did good is that they also tried to train the model based on the transformations too, and they wanted to see the performance, and still IT performed better. Yes. So if we conclude this part, we see that IT is also generalizing more according to this task. So far we had selectivity and generalization and tolerance better in IT relative to before. But this was all in the population level. And the last thing that they showed is they were trying to explain the population behavior based on the single unit properties that they suggested of explaining. So, for example, one of them was the ROC. So we talked about it in class, but the area behind below the graph of the ROC, they measured it for the neurons, and they rank ordered it. So that's like here you have you don't have a lot of area below the graph, and as you go, it becomes more area. So they saw that this property, single unit property, for example, can explain tolerance. I mean, as long as if you have higher values, you have more tolerance.
So each point here is what?
Okay, so they had a sliding, they had a sliding window of 48 neurons, and they took, for example, 48 neurons with a really similar ROC area, and then they did this task, the tolerance task, on this part of the neurons, and this is what you see in the graph. So another thing that is yeah, sorry.
Each neuron, I think you should go and explain exactly what you mean by the ROC. You have to tell between one stimulus and another, right?
Yeah,
what are
right.
The two stimuli
I
take
forgot
your
it.
time and explain that.
Yeah, sorry.
It's important to
Okay, so the ROC was computed for the best. Okay, for each neuron, they wanted to find the best stimuli, which is it responds to really above baseline. Okay, so they did it for each one, and for each such a stimulus, they wanted to find ROC.
So there are 50 pairs again. 50 pairs. There's one stimulus which is sort of elicits the highest firing from that cell. They take that one and compare it to the
50?
pairs.
No, now we are in the transformation task. So we have 6 transformations for each object, and we have 10 objects.
Okay, so it's a so this is at the level of the transformation when you sort of take the same object and you shift it.
Yes.
Okay.
So they took
What
the 6
transformations
transformations.
are they talking about here? This is position.
And these ones, yeah, the scale, the position, and the context. So okay, so they in the ROC they measure the 6 transformation of the best object for this specific neuron versus all the transformation of the other objects. And this was the ROC. This was, I mean, the area below this graph is the one that you can see here. That they suggest is a good predictor for the tolerance of the population.
I'm still mixed up. Because, okay, when you have an ROC, typically you have one stimulus and another, right? And you say, okay, how well, let's think for a minute about the motion, and you find the parallels here. In the motion case, you said, okay, the cell has to tell if the movement is to the preferred direction or the null direction. So you have two distributions, right? And we looked at the sort of the overlap between the two distributions, and we changed the criteria and said, okay, what is the area under the ROC, meaning that you change the criterion in a sort of in a gradual manner, right? And then the higher the area under the ROC, that means that the two distributions do not overlap, right? And it's easier to tell, okay?
Yeah.
So the ROC could be between 50% or 0.5 if there's no information to a 1, right? Just will have sort of the values that you can get. Okay. Now, in this case, what did they do exactly?
I'm not sure I understood what's the difference. Like why what you say is different. Can you?
Okay, so the values here are okay. ROC does not get to 1. It's about it's a mild increase of the ROC, but you know, okay, 75% means that the cell does convey information about what the stimulus was.
Yes.
So you're comparing two. ROC is for comparison of two stimuli. What are the two stimuli again?
So it's not exactly. I mean, it's two groups of stimuli. This is what they said that all the 6 transformations of the best objects that the specific neuron responds to.
So say the giraffe. Okay, giraffe compared to what?
So all the giraffes compared to the squirrels and all the, I don't know, other animals.
No, probably to something, to the scattered picture of that same giraffe, because there's pairwise comparison.
No, but this is tolerance. The scramble was in the selectivity.
Is that you take the different giraffes, okay, when you move them, right?
Yeah, this is versus all the other objects. This is what they did.
Okay. Yes. Okay. Time out. Okay.
Okay.
Hands up. Okay.
Should I do something? To conclude? Okay. So we saw that IT had a better both tolerance and selectivity than V4, which is what it matches what they suggested in the paper. And also we saw a little bit of single unit properties that could maybe explain the population behavior. And that's it. I'll try to do that.
A few minutes for sort of a general discussion for Anthony. Right?
Yes, absolutely.
Okay. So let's go back to your conclusions.
Okay.
which is most important. We started talking about, single
I thought
unit.
I
I think
finished.
this is something that I want to sort of understand with you. Would you expect, that the fact that IT has a better generalization than V4, it seems logical that this would sort of be single unit properties would be relevant for that. For instance, okay, let's think together about this. This is not just for you. Let's think together. What would be, so she mentioned a bit something about the single unit properties when you compare V4 and IT. So one thing is what?
Receptive field.
Receptive field.
Obviously, if you move it around, if the receptive field is bigger, it makes sense that those neurons will be more capable.
Absolutely, absolutely. And the next thing, which you did not refer to, but I referred to in my talk, is when you look at, at higher along the hierarchy, the specific features that drive the cells become more and more complex, right? So that's logical that it would, if you're using a vector with such elements that you are going to encode information better than if you are at low level.
Although it's somewhat the opposite to what we're saying about the tolerance, because, being tolerant, you have to be activated for the features in this side of the receptive field, and maybe it's the same composition of features, but still it's very different places at V1.
Right, absolutely.
So it's cool.
Yeah.
Sort of opposite, but they still can both get stronger,
Right,
but
right.
different.
Right. So by the way, I don't know if you've heard Svirov, who's also, an advanced student of LSEC. He's done, in my lab, a project in which we looked at a similar sort of question in terms of, okay, how much information about, what is information about the position of the stimulus, irrespective of what it is, and lo and behold, you'd find that this would be most significant in early visual cortex in V1, compared to what is the identity of the visual stimulus in terms of how do you grasp it, first of all, what the object is, but also how do you grasp it, and something like that. And that sort of mapped into parietal cortex and into sort of ventral areas which are sort of corresponding to infratemporal cortex. So again, this is something that you can see, and whoever's interested can come and hear from me a little about this, but you can see this also.
And his work was on humans and fMRI?
Yes. Okay.
So
Which
IT
leads us, yes.
is very tonotopic.
Excuse me?
It's very retinotopic. IT.
Not very retinotopic. Typically, receptive fields are big, so once the receptive field, I think,
Once they're
yeah,
big,
okay, yeah, that's great. I think she just glanced over this. Okay, so the red here corresponds to where the stimulus was presented. Okay, so I think it's important that you don't want to present the stimulus outside the area in which the V4 neurons are responding, because then you're going to put them in a disadvantage to start with. So the comparison would not be very viable. So they've used a sort of a stimulus which excites both V4 neurons and IT neurons. But if you look, the receptive field,
there would excite very little.
some of them are very selective.
Population. Even the biggest receptive fields, they don't even grasp, a quarter of the red area. So if you present this.
Right, so they see just a part of the, right, like an aperture, we talked about this, right? There's an aperture seeing just part of the image, not all of it, while if you look at the, IT neurons, each circle is one neuron, okay, so they encompass, most of them encompass the whole stimulus. So that's a difference between the two, which sort of suggests that why would you have greater generalization in IT than in V4. Okay.
By this, mostly
Because if you go into the textbook, now we can teach that along the ventral values, you get more generalization and.
I think mostly yes, but
If you're convinced, the problem is.
I'm not sure about some little things like when they showed only the position. Like there was stuff that were a little, and also the selectivity task. I think it was good, but it's not that I have a better suggestion, but I'm not sure it was like the best task for selectivity. But I don't know enough
by
to.
the way. If you look at the graphs again, how well do you do when
This
you're?
one?
Huh?
The selectivity?
Yes.
Yes.
So it's a monotonic function as a function of the number of neurons. But what do you expect if you are to increase the number of neurons? Would that saturate? Would that, not that I have an answer. I'm thinking together with you. I mean, the question is really how much information, access information do you get from the new neurons, right? In terms of so the question is how sensitive, which refers to the ROC curve. I mean, how sensitive are these specific neurons to their different images, right? And how noisy they are, okay? Because if they're very noisy, you may introduce, if you increase the number of neurons to have 15,000 rather than the most selective 150, you may actually introduce noise, and this may actually saturate or even go lower than that. So it's a question here. I think it's problem solved? No, not solved because of that,
that's
right?
my question. If you are one of these great
I
students,
answered your question.
and
I'll sit in the back with you.
you want to study the visual system, is this an open question? Or to what degree is this generalized over the, I mean, what's new? This is a 2010 thing. I draw, when I was a student, I knew that as you go higher, you get more general.
Yeah, that 2010 is when optogenetics, probably the first papers of optogenetics started. So it's saying, okay, what happened in the monkey literature in these 5 or 6 years since then? So there's been, I mean, we'll hear something which is related to that. I don't want to take too much time. Thank you very much, Tom. I'll go to the back. Okay, you need help setting this up?
I hope not. I don't want to exclude it.
So next, we're going to hear something about sort of similar topic, but we're going to hear a paper by Nicholas Kritzko. They're even older than that. There's been some advance in that, but I think that's a relative classic. Comparing, again, vector representation. We're talking about the population representation, and Nicholas Kritzko was able to record in humans, doing functional MRI in humans, using the same images that Keiji Tanaka and his group have used when sort of recording for monkeys. So they have now we're going to see a comparison between sort of the population code that you get for a given stimulus in the monkey with what you get in humans. And remember that there's also, you're using 2 different methodologies which are also distinct in terms of the spatial and temporal limitations. So it's an interesting, okay.
What's the right thing on the this HDMI?
I'm sitting in the back. James by Aziz.
So far, what I have a clock in front of me. Do I have a clock there? Okay, the stage is mine. Like completely mine.
You're already 4 seconds into the.
Okay.
Go ahead.
Okay, very nice. So I just want to start with a small disclaimer that I take many questions from the student. I want to have like a more lively talk, but I don't take any questions from the professors. Yes, because I want us to remain self-confident during my talk and not get confused. But of course, the professors might feel that I'm not explaining anything well, and they might want to point a certain point out, so they can ask the students if they understood.
No, not
Yeah, and of course, if they don't understand, they can ask me. That's not a problem. Okay. So now our topic: matching categorical object representation in inferior temporal cortex of man and monkey. Okay, I hope you all read the paper, at least the abstract. Okay, very nice. Okay, so yes, that's where we are, man and in monkey, and as you all know already, so we are the inferior temporal cortex is generalizing things, and that's of course that's why we're searching for object representation. And now we want to compare man and monkey, but we also don't want to compare only man and monkey. The big chiddush here, the big new thing is that slight, which spiking vector. So you have one type of data, then a completely different type of data. Okay, this approximately the same region, you were searching for the same thing, but how do you compare? So during my talk, for the comparison, I will use the board here for some math later on. I hope not to confuse you, but to clarify. Is there anything which I can swipe and step my white shirt?
I need the professor to
Maybe it's
get
behind the
Your answer?
I can give you
no,
my
the
shirt.
white, Daniel, behind the white screen. Just lift it, the screen.
String?
The screen, lift it, maybe it's behind
Yes.
somewhere.
Come back, though.
Okay. I just want to have feedback when you don't see anything on the board, especially this row. From my experience, there is like a lower limit here of seeing something, probably around here. Okay. So, so first of all, I want to go to the experiment and start with the paradigm of the experiment. So there were pictures presented to the subject. That's two monkeys and a few people. And in people, the people were lying in the fMRI. A monkey had some electrodes. Well, we usually don't pick so many electrodes in people. And yes, and that were the pictures. So you see they're categorized, and in the end, the nice thing we'll see these categories within the patterns of activity. So the symbols were presented a few seconds in a randomized order in both like man and monkey. It was according to them was super randomized, was super calibrated to the amount of time, so there's no kind of special effect due to fMRI study or electrode studies would interfere. And then they acquired the data, and they then made a very nice thing with the data. So that's a dissimilarity matrix. Okay, so I explain first on what's this dissimilarity thing, and yes, and what did it define? So first of all, you see there's some nice patterns. So nice patterns here, you see there's some shapes, there's 4 blue squares. That's a nice thing. As you see, I found something. If your data is not completely random, so that's a nice thing. And if you see, need a long stick. It's also somewhere. Pointer, okay. Very nice. So as you see, if you compare face to face, okay, so we are talking about dissimilarity. So if something is has 0 dissimilarity, that means it's very, very similar. So if we have faces and compare human faces to human faces, they are all very, very similar.
In what?
In their patterns of, let's say, patterns of activity. In monkey, as here we have the electrodes. In human, we have the fMRI, the voxels, and so what they did is that within the data, so the patterns were also mean. So there was so every, let's say, comparison point was the mean data from one picture versus the mean data of the other picture. So that was the point. And now you see how similar or dissimilar are those. So you see faces, are very similar to each other. Okay, of course, if you have and you have also human faces and even non-human faces, and you have monkey faces versus human faces, very, very similar. And that's the 4, let's say, really, really extreme categories. But they will see also some more findings, which will have the next beautiful picture. So that's basically the summarizing picture of the whole experiment, which explains everything. I will spend probably almost the rest of the time explaining this picture. So, can you see the pictures on the picture? Okay. So there's also some coloring. So, as you see, they concept that I will discuss. That's the whiteboard here. And so first one was what was fine after making a little bit of math and having this beautiful picture. So you have here in red, yes, very nice, all the faces together. Together means they are very similar and they're distant from the other colors, distant from the other dots. This means they are very dissimilar to the other stuff. Then you have here the, let's say, body parts or animals here in this purplish, yeah. And then you have this non-animate like food or tools, which they have like some natural objects and artificial objects, but they're pretty mixed, let's say. This light blue and blue. But the good thing is that the light blue and blue doesn't mix with the red and doesn't mix with the purple.
Daniel, I have to stop you.
Yes.
Do you understand? That is it crystal clear to the class?
What is being shown here, okay, to the class?
Not you.
Okay.
Let's see if they.
I want to have questions.
You see some images, right? And you cluster them in some way. How did you cluster them?
Ah, very nice. That's the best question ever. Now we're going.
I want them to answer if they understand, if they can explain, any of them can explain the slide before.
Can you go back?
You need to go back a little bit. So, I don't expect to explain the slide yet. So I just want to report the findings, yes, first in this slide, that there's some nice things, that things are similar things in objects are clustered together. How it was made, I'll explain exactly now. And after this slide, I ask you back what this.
Go ahead, no problem.
Okay. 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 Yes. So, as you know, we have already, let's say, mean patterns of activity of voxels versus voxels, and the recording gauge and the monkey. So the firing weight versus the firing weight. So when you compare, when you have like this vectors, you can compute, let's say, a distance of the vector. So they're having the covariance. So we have here the Pearson correlation, coefficient. Who knows the Pearson correlation coefficient and can explain it to the class? Oh, very nice. So I have now something to do. Okay. Pearson correlation coefficient is a measurement how linear arranged are the data. So if the data look like this, so we can draw a line through. So Pearson correlation here is very high, it's 1. If the data is like this, very nice. The absolute value of the Pearson correlation coefficient is also 1, it's exactly -1. Because we can draw a line for the data. The data is dependent, right, in a linear manner. So the more interesting cases is, okay, so it measures the linearity of the data. So usually the data is of course not in a straight line, but it's something like this. So we still can draw more or less a line through it. But it's, of course, the data is not exactly on the line, so it's, you see it's positive, it's maybe close, somehow close to 1. But, yeah, I would say, I don't know, what's a good value for that? Maybe it's 0.8. Okay, just an educated guess. Okay, so now we know how we can compare two vectors, yes, and we can like use the correlation, like the similarity with R or 1 minus R. And there you see some big formulas for these R's. And okay, but now we have a lot of vectors. Yes, we have like these images. We have these 64, 96. 96 I think images. Okay, so if you want to compare, let's say, all images, like how much is every image similar to the other images, so we have animate, inanimated, and human, that's not, let's say, the mind, it's not the mind clustering the images, yes? So we don't say, okay, how really the mind perceives this image similar to that image. We don't see it. That's like how we arrange the rows in the columns. The question is, okay, how does our mind, the monkey brain or the human mind, does arrange the rows and columns? Maybe, I don't know, there was in the beginning some images, see, which have this like strange signs, like a star, or there's this A in the face. There was a back of the head, which this should be this picture. This picture should symbolize a back of the head, and it was perceived as an ambiguous thing. I don't know. For me, it looks more like a coconut, and it was really perceived by the subject like an ambiguous thing. So yes. So the question: how does the mind cluster these images? Not how we, like, as the designer of the experiment, clusters it. Okay. And this picture remains okay. There are some there are some correlations of the cluster how the designers of the experiment and the mind clusters is, as you see here very clearly. Okay, but now I want to really see in the data. Yes, how in the data. So how, and then we want to make a multi-dimensional scaling. We want to reduce from this 96-dimension matrix to the beautiful picture. This which has like the two-dimensional scale. Okay, so if we have just two pictures, and then we have banana versus face. Okay, we have a point and we can scale it in two dimensions. How much banana is and how much face is. Does anybody see this picture? Okay. So, okay, if we maybe add a third dimension, banana, face, okay, tool, scissors, we can ask how much scissors is. Okay, so the question is, how do we then, okay, and then we have, let's say, some data points, which can tell you in 3 dimensions how much scissor I am, how much face I am, how much banana I am. Okay?
Is it the distance between the images?
Yes, the distance.
Okay.
And the distance we already know, Pearson correlation coefficient. So now there's another thing they say the distance, that you can compute something like Euclidean distance like. So there's the stress, there's something like Euclidean. Euclidean, everybody knows what's Euclidean distance, Euclidean light distance. Okay. I see nodding. Thank you for some feedback. I also want some questions from the audience, okay? I mean, there will be discussion. Very nice. Question.
Just for me to understand if I understood correct.
Very nice.
So they clustered the pictures according to the correlation between each picture, and they did this is they reduced the dimension. They did this correlation in multidimensional hyper.
Right. There you see all the dimensions, right?
And then they somehow reduced the dimension, and they got only one dimension, which is this picture we see there. It's still
Right. They 2 dimensions. You see, like you don't have a line. You have in 2 dimensions, 2 imaginary. As you see, there's no scale of these dimensions. I explain why there's no scale. Like usually, as a good, if you publish a picture, okay, so say what's the white scale. Why don't they have some white scale here? So, and that's why I'm exactly drawing this image and doing some and pointing some data points here. Okay. So here you see some data points, and now you want to reduce from 3 dimensions to, let's say, 2 dimensions. So you see, you can explain the variance of this of the data points. The best thing by drawing maybe a line, something like this, through the 3 dimensions, and maybe also like this. So now we have 2 more axes, and the question is, okay, what do I write on the axis? I write it banana-ish, face-ish, and a little bit scissor-ish. Because you make you do axes which combine, let's say, the 3 features to 2 features, and in our thing it's from 96 features into 2 features, because you take into account of every feature, how much it contributes to the similarities. And then you draw something like, say, this imaginary axis for the 69-dimensional space, and you take the two axes which describe the most of the variables. Yes? You can describe the most of the dissimilarities. Yes?
So it's basically like PCA.
Exactly.
Taking two main vectors, right? Of it.
Exactly. Oh, that's nice feedback. I want to have more feedback like this. Okay. So now you see why you didn't label the axis, because it's a combination of the 69 pictures, a little bit of each of one, and now and if you take the two main dimensions, so now you can really explain. So these things are clustered, yes, and you can say. So now everybody of you can explain this picture, except the thickness I didn't explain yet. But there's the upper pictures, this two things. Everybody can explain it. Now I hope. Okay. So I can ask everybody precise questions about this picture.
Absolutely. You should.
Okay. So now I want you just to backtrack. Okay. Does anybody see this banana? Okay, and this face here. Okay, there are some faces. Okay. So, can somebody? Okay. So, what does it say that this banana and the face are so far apart? On this picture, what was the experimental finding that they now drew in this nice picture? That the banana is there and the face is there.
They are represented in very different ways.
Right. In monkey, banana is something very, very different than the face. Yes? Bananas are like, banana. Yeah. Like in humans, banana is like banana. Not like, who cares about banana? Yeah? I feel like almost like a face, just like not so round. Okay? But banana is very different in monkey than a face, okay? Everyone understood?
Is it a monkey personal? Okay. Is it can I generalize it to a general monkey quantity, or is it based on single monkey and
To a
is it a
monkey.
single
Okay,
graph
so I think
monkey?
that's a very nice point because we're already going through the discussion. Yes, and I think.
Summarize and close up and do that.
Okay, so yes, so there were just two monkeys. So to say every monkey is like this, if a sample of two, I think it's up to the interpretation of the author. I would say, okay, you have two monkeys and you have kind of, let's say, clustering. It's an indication, but I don't know if you can really say for now published, put it in principle of neuroscience, monkeys have something like this. Okay, so I summarize. So that is the main picture of which I wanted to explain. Then there is like they also did a clustering algorithm, which says the same thing, but just like with a nice tree. And I think the next few slides will be for the discussion. Yes. So but I mean the conclusion basically everyone understood. The IT does cluster things. Yes, we see that the patterns. Yes, are the pattern of activity in the IT. Show some clustering of things. So there might be an inherent, human and monkey inherent categorical perception of things and pathways or activity patterns which are specific to faces, to like non-life objects.
Daniel, what is the width of the line connecting between human and
Yeah,
monkey?
what are the lines? Okay.
Right. Thank you very much. So the lines are basically how much difference is between the monkey and the human. So if we have like thin straight lines, so it's like so there's like it's like the same it's like in the same space. But if they're like a thick line, so that's represented like very differently in comparison. Like the human space and the monkey space. Yes. So as you see, you have kind of, let's say, not a total, let's say, randomized connections. Yes, but you have like many straight lines or straight-ish lines and many thin lines, that it means that the presentation is rarely similar, yes, between the human and the monkey in this abstract space.
Is that surprising, or is that something you would have expected? Okay, let's have a discussion on that, because that's really the key issue here, right? I mean, that used a very different methodology here, and if you go back even to the slides before that, where you showed just the correlation matrix, because that's really the raw data, right? I mean, when you sort of had to transform it to 2 dimensions, and you had to do some the multidimensional scaling, of course, enforces some stress and change in raw data. But this is really the raw data here. And just looking at it, that looks quite similar, right? And the question is, what do we make of this? I mean, how do we explain this?
Maybe this is, I think, a really cool method of looking at it, because instead of comparing the data they got for each picture between fMRI and electrophysiology, they said, okay, these are different methods, but we can still compare the results that, the relationships between what we got in each case. That's why looking at the similarity or dissimilarity is a really cool way of comparing very different methods. So
Absolutely.
that's the major
So
thing
the
I
key
like.
thing here was just to use the same stimuli, right? First of all, use the same stimuli. But then, do you find that, first
I think
to you, Daniel, and to the rest, do you find that surprising? Is this something you had expected? What do you make of that?
I think 2 main issues. One is that a lot of the research is made on monkeys, and we kind of conclude things about humans, and they come to show that it is similar, surprisingly, even though you use different methods. And the second is that evolutionary conclusions that have been made about the visual system of monkeys, and then that they actually have something that is similar.
In the back. Okay, so you're saying, okay, not surprising at all, because, okay, Darwin said that we evolutionary tree, and closer to monkeys than to fleas, and therefore maybe our representation is going to be quite similar. But I want to stress 2 things. First, remember that, the fMRI signal is an average of the order of 1 million neurons, right? So you're talking about a completely different scale here, which maybe you have not thought about, but you're talking, as I say, 6 orders of magnitude. Okay, so you're computing a vector, one from 600 neurons and one from 600 voxels, and each voxel is the average of 1 million neurons, right? And still, when you look at this, you get a very, quite a similar representation. So that is, what do we make of this? Is this something that, irrespective of the scale at which you look at activity, you're going to get the same results?
Not
So just scale,
irrespective at all.
that's a just scale invariance, right?
No, but it says that
And
the 600 neurons are the represented,
so maybe the 600 neurons are representatives, are sort of representative
of the voxels.
of the voxel, right? So but that's just indeed a scale invariance. It's like you were to do a poll,
But
okay?
it's not that
And
it
look
takes
at,
two
what is, how many, politics, who's voting for this party and that party, and independent of, the scale at which you're going to do this, you're going to get the same results. So that, I think, is very, very interesting. It sort of validates again the fact that, okay, it makes sense to use this fMRI signal. But there's a lot of things that sort of come up that I did not expect this. First of all, because we as humans, we categorize, for instance, images of humans to us are sort of, we recognize individual images, right? For one thing. And we have language, so we have some semantic relationship between one, we call these fruit, banana and a pear and a kiwi. Some of the images are most likely not something that would make sense to the monkey, right?
They actually show the same effect if you remove the faces and the whole spaces and places. So even without it, you still.
Okay, but we have a whole level of semantics. Leave the faces alone. Okay, faces is one aspect, is that we can individuate faces, but the other is that, okay, this has meaning to us. This has meaning to us. Does not have a meaning to a monkey, irrespective of just language. Okay, are we running out of time? And
Yeah.
okay, so I think this is a cool experiment. Just to sum up, it's a cool experiment. Uses the same methodology as before, and it's an interesting comparison between the 2 levels. It's between 2 species, and also levels of scale, okay? And, you know, what I would think is really something that's necessary is to do this in a monkey, where you're sort of, okay, now what's more important here? Is the aspect of a change in the species or a change in the scale, okay? So you wonder, okay, if you were to do this in a monkey, you could, you know, do this in the same species and just control for the aspect of the scale. Because there's something about scale invariance which I find extremely interesting. I don't think it has been followed yet, but it's really something to think about. Thank you, Daniel.
Thank you very much. No, just like my personal comment on this, so I like this paper very much, but I didn't find it, like, say, very surprising. Especially like in Gemara Bava Kama, it starts with let's say, different, let's say, types of damages. And then it sounds like, okay, it has a different, like, ideas. Why does it have, like, the Mishnah elaborate in certain categories? And says like that, okay, that it has to list all the different, like, say, kinds of, like, the pit and the fire and, like, a living ox. Because if the Torah would write just, let's say, one category, would think, oh, the non-living objects or living objects are completely behaved different, because humans have, let's say, at least according to the Torah, different representation of animate, the yesh bo ruach chaim, the ein bo ruach chaim, of animate and inanimate objects.
And so do monkeys. I mean, what we see is that so do monkeys.
Exactly. And
but it's not just that you have a division between animate and inanimate, but you've shown, if you go back in the slide, in terms of the lines that you drew there, here, that, you know, the representation is very similar. I mean, if you compare these, okay, where is the banana here and there, and you compare, I mean, this captures this, right? So if you have straight lines here, means that you have the same representation, right? So lo and behold, it looks like you have the same representation. That's something that I would not have thought that you would find.
Yeah, no, it's at least let's say, I mean, if you want to connect on this connection, okay, so that's like the beautiful connection of the human and the monkey that's so similar, actually was from Hal talking about. If you want, yes, because no, I just wanted to have this little spicy up thing, because according to Ramchal, like say the lowest soul, the nefesh, is a physical thing, so which is like totally in a physical way and can be explored by science. And that animals and humans have the same type of, let's say, animal soul, of the physical soul, which you see here beautifully is very similar, or let's say this type of soul is physical, which you can actually measure with data. And yeah.
Okay, so
So I like it very much, this picture.
I would not argue with that, okay?
I wouldn't also argue with Ramchal. He is much better than us.
Yeah, let's take a 15-minute break. You have the time to sit, to get everything ready, and we'll continue. הפרצופים הם דומים אחד לשני ביחס, השאלה הרדוקציה שראשים איך הם ביחס, כאילו יש לך את העניין של איך הם ביחס לכל הדברים האחרים.
אז יש לי קשר סקאלה?
אני חושב, במידה מסוימת, קשר. אז למשל, התאים, נגיד, אם התאים הם מגיעים לפרצופים, בלי שום קשר לפרצוף או לא פרצוף, כמו שראינו בהרבה מאוד דברים, אז הם יהיו כולם, לא משנה, איזה פרצוף, כולם פרצופים שיהיו אחד ליד השני. ביחס לתמרור או ביחס למשהו אחר, הם יהיו ברור. כן, זה נובע מזה, אני חושב. מה הדאטה סט של הפרצוף? לא, אז כן, הם רשמו שם ב-IT.
לא, אבל כאילו
אבל עצם הרעי. זה לא רק את אותו סוג, כולל... לא נחשב מאוד של... מה? כן, 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 כן.
That's actually the only thing I noticed. You were like, I mean, you weren't talking through your slides, which is good, but you were sort of like talking to the pictures that were walking.
How much is the pattern? How much is the pattern of the different? So you have on the yes, yes, on the one side, the test, you have O1. On the other side,
much now. I don't try to pick up the car.
Can you compare the two vectors?
a nivel de studio de pensar realmente la dinámica de los
Every effect, every cell effect.
Mani attende, quando lo scrive.
I've written people in more.
Yeah, it was
So
fun.
like,
At the end, I made like some religious jokes. I don't know.
There were jokes all over
you took a lot better than the test that you got off in.
Exactly, that's what I mean. I mean, obviously, you can always improve that.
I just couldn't resist. Behind the stage, I can encourage people.
Yes, avocados also.
Now you're searching what's the purest word? You want to search the purest word?
No, I want to make videos.
Yeah, absolutely. No, you're not learning from it, yeah. In physiology too, it's all about feedback system. No, but it's true. No, you practice and you do it a lot. And I think you made a very good start. You're still smiling, so it must be good. Yeah. Yeah, so keep it up. Yeah, of course. Seriously, if you want to organize another one, I'm around.
Yes!
Awesome.
I got a notice from one of my lectures saying when we have
focus on myself, especially since I'm so stressed out.
Okay. Next. ואת רוצה, הנה יש לך פה. רצוי, גם את. You have to. No.
Okay. Okay, so I'm going to present a paper called Context-Dependent Computation by Rika. You really can hear? Okay. I talk like I don't have a microphone. Okay. I'm going to present a paper called Context-Dependent Computation by Recurrent Dynamics in Prefrontal Cortex from Newsom. First, I want to start with some introduction to what is a prefrontal cortex and what is its role in the behavior. So, prefrontal cortex is a region in the frontal lobe. It's most of the frontal lobe, and it has a role in a high cognitive function. And in most of the high cognitive functions, I have some region in the frontal cortex that explain them. Here in this graph, we see attention in the human brain, and the behavior is like the decision making. We're going to focus on decision making, but in the monkey brain, which our recording will. Okay, good. Okay. So the recording were taken from the arcuate sulcus in the macaque monkey, and we believe that this is actually the region that is responsible for the decision that were made in this task, but this is a new task, so we don't know it for sure. Okay. So how does the prefrontal cortex relate to vision, which is actually our topic? We want to discuss if, in cases when we have to make a decision which are based on a complex visual stimuli, we want to know if the visual stimuli is separated already at the level of the visual cortex, or the entire visual stimuli reach the prefrontal cortex, and only then the relevant information is separated from the irrelevant information. So this is a question that they write, but the reason that this is an important paper is the method, the way they explore this question. And we're going to see a new interpretation and a new approach to explain the behavior of a neural population. And we're also going to see a model, a neural network that explains how a decision can be different in different contexts. So what is the task that we defined in order to solve this problem? To differentiate between the two hypotheses we defined earlier. So we have two monkeys, and the monkeys should fixate on a point in this point. They saw either a blue cross or a yellow square, and the blue cross is the color context, the motion context is the yellow square. After less than a second, they see a stimuli of moving dots that have two colors. In one of the monkeys, it
it was red and green, and we're going to focus on this monkey because the other monkey has problem with colors. So monkey A, our monkey, saw moving dots in red and green, and if it was a color context and most of the dots were green, you should make it cut towards the green dot at the left side here. And if it was the motion context and most of the dots move to the right, you should make it cut towards the right dot. In this case, it's the red, but it could be the same, it could be different. So we have different coherence, both in the color and both of the color and of the motion. And what we mean by coherence means that most of the dots, a very large fraction of the dots, was green, or a very large, the ratio between the red and the green was large, then it's a strong coherence. In a weak coherence, where the numbers were quite similar. And the same about motion, a large fraction of the dots moved towards the right. It was a strong motion, motion coherence towards the right. And in the right graph, we see that the monkey had learned task. We see its performance and okay. We see that in the motion context, the motion is going to be represented in black. If you see blue, it's color. If you see motion, it's in black. In the motion coherence is this side of the graph, and the color coherence is this side of the graph. And in the motion context, only the motion coherence, not only but mostly the motion coherence, affects the performance of the monkey. The color coherence changes slightly, but it stays on chance level because half of the cases the monkey saw a high color coherence, which high motion coherence towards the right, and in other cases it saw the motion towards the left. So it should be about half of the cases in each of them. And the same in the color context, we see that the motion coherence that changes the performance slightly, but mostly it's the color that affects it. So we see that the monkey learned both the context and knew to where it should make it a cutoff. Okay. So now we get a little bit deeper in the data. So here we see the responses of 6 neurons. And for each neuron, the choice one was defined as the choice that he liked most. And we see that the behavior is dependent on the choice, on the motion, on the color, and the context. Each of them has some effect on the variant of the neuron. So we want to identify how much any of these parameters affect the variability in the responses of each neuron. So we define the regression coefficient. The regression coefficient are the coefficient of the parameter that we checked, and each coefficient represents how much the choice coefficient represents how much choice affects the variant of the neuron. The motion coefficient explains how much motion causes variability in the variant, and etc. So they did some.
So let me just understand. So you say, okay, the neuron, you give a given stimulus, and the monkey makes a choice. And there's a given stimulus has motion and a specific color parameters, right? So motion and color. The monkey makes obviously a choice at the end, and there's a context. Whether was it a color test or a motion test? Okay. And now you get basically the variance of the firing of the neuron on a trial-by-trial basis, right? And you're trying to explain that variance with this regression, right?
Yes.
So you get parameters of how important was the choice, the motion, the color, and so on for that specific neuron, okay? And you see just examples that, the neurons have, there's effects of all these aspects, not all of them, but a lot of them, and that can change from neuron to neuron how much is the weight of one aspect versus
actually will explain also what are the lines here, because we have a complicated graph later, so to make it simpler, it's best if you miss those terms now. So the darker black line here is the strongest motion coherence toward choice 1, and the darker black here is the choice motion coherence toward choice 2, and in the lighter gray are the weak motion coherence in the middle toward choice 1 or toward choice 2, and the same about color. And here we see in context, we see the color and the motion. Remember, color is blue and motion is black. Okay.
So basically, this is just a response, right? This is the
Yes.
x-axis is the time, right? It's just the
Yes, it's
response
the
to give-
responses, and then we want to see how much those responses are explained by each of the parameters. And in here we see the regression coefficients. This is going to be what we refer to like the neural responses. We are not talking any longer about the firing rate. We just talk about how much each parameter affects the variability in the firing rate. And here we see the recordings from the prefrontal cortex. Each square is referred to one red dot here, and each square has many little squares inside, and each the color represents the regression coefficient of the choice, of the motion, of the color, and of the context. And we see that in monkey eyes they seem to be uncorrelated, and here we see the correlation between the regression coefficient in the choice axis and the regression coefficient in the motion axis. So how much the variability is explained by choice and how much the variability in function is explained by motion. And we see that they are uncorrelated, say so.
But that's across the population, right?
Yes.
The dot here is one neuron. Okay, so it's the regression coefficient for one neuron.
Yes.
Choice and motion, right? And overall.
Yes, and also time, and it's just a generalization over trials. Okay. So those axes are also very important for the next graph. So we have the motion. By motion we mean how much motion affects the variability in the firing rate, and we have choice, and this means how much choice affects the variability in the firing rate. And the same about the color axis. Is it clear? Okay, good. So in this graph we see first each dot here represents a point in time, and as we say, the black filled points are the strongest motion coherence and toward choice 1. Only correct trials have been calculated in this graph, so in case we have those three choices, we will have only lines in this part of the graph, because in the correct trial the monkey would make choice 1. If he would make choice 2, it would be a miss, so we would ignore this trial. This is the motion context. This is the color context. The upper part is motion context, the lower part is color context. So in each trial we have both the motion coherence and the color coherence. So even in the motor context we can refer to the color coherence in this specific trial. But in the color coherence we have all the coherence at each side of the graph, because the choice should be referred to the motion and not to the color. So we can make either choice 1 or choice 2. Okay. So here we have the choice axis, which means how much the variability is dependent on choice and is explained by the choice. And here we have the motion axis, and we want to see how much we can explain the variability by the motion. And we see that in the initial point, dots on, that means 100 milliseconds after the stimuli was shown on the screen, at the beginning, nothing explains the variability, but then there is a fast increase in how much the motion explains the variability in the motion context. And as time goes on, the regression coefficient of the motion decreases, and the regression coefficient of the choice keeps to increase until the monkey makes a choice, and this region refers that the monkey had made a saccade toward choice 1. or make a decision to make a saccatoral choice 1, and the same here to make a decision to make a saccatoral choice 2. So we see that there is an effect in the emotion context. There is an effect of the motion about the Fahrenheit, but also we see effect of the colors on the Fahrenheit. In this intermediate graph, we just see how the motion currents. We separate the data by the motion currents, but we see how the colors explain the variability. Okay, is it clear? Good. Okay.
Wait, I have a question here. I'll ask as Daniel said, I'll ask the crowd here. Okay, explain to me what is the, a dot here, what does it mean here? If it's all clear. Adi, you can also.
Value.
What is it?
In space of.
Right, so first of all, it's phase space here, right? It's dynamics, as Leah mentioned. Absolutely, it's phase space of what?
The coefficient of the
Gradient of that is.
So the first thing, it's a population response. It's not one neuron here. It's a population response. So you think you have a vector for each time, right? And you're asking, okay, how much of this vector that you get across the population is affected? There's different choices, right? Or the motion, right? So you're asking, okay, you presented a stimulus. Now the stimulus could be at, high coherence or low coherence, let's say high coherence upwards, okay? So how much of this vector of activity that you have is affected by the fact that, the motion changes, okay? So notice, first of all, what do you see? I mean, the dynamics here, let's stick to this one, and if you want, you'll take the lead here, but let's go over this and explain, what do we see here, okay? So because now that we understood that this is a vector, a trajectory in time, what do we expect to see? First of all, it gets to some, so notice that this is the motion axis, this is the choice axis. Take your time and explain this, because this is important.
Okay.
Let's go over this, if you can.
Okay,
because it is difficult.
Okay, so I'll start with explaining A, and then I'll explain what changed between A and B. And
yeah, start with
okay.
Take your time.
So we have in each trial we have multidimensional data about the motion coherence in this trial, the color coherence in this trial, how much the variability could be explained by motion, color, context, and choice, and the point in time that all of this was happening, and that's it, I guess. Okay, so this is a very high dimension data. So we want to represent, and we also want to represent four of the 6 dimensions I mentioned. So, we also have the context, the 7 dimensions. Okay. So here we represent the context. This is the upper part. The motion coherence is represented by those dots. Time is from the beginning to the end. It's not the axis. It's just because there is changes during time, then we can see how the time. If they're all in this case,
The time is constant.
Yes.
between every dot, the time is constant, but like you see here, the distance between them is not, because the plane is how much the variability is explained by each of the parameters, and if in 2 points in time the variability is explained by the same parameters, then we're going to have a very close dot. So we represent the motion coherence, we represent the context, we represent the time, and we present how much the variability is explained by only 2 of the coefficients, by the motion and by the choice. And we see that at the beginning, in the motion context, in the strongest motion coherence, the variability is explained by the motion. And after a while, the motion can't no longer explain the variability in the Fahrenheit, and the choice that the population was tending to is what the thing that explains the responses of the neural population. And we see that as the coherence of the motion increase, also the effect of the motion increase. And the same here. Now in this is part A.
Before you move to B,
Okay.
let's finish here, because notice where do you get to when the dots are off? Okay, so the monkey has to integrate the information, come up with a decision, because it's a motion context. Was motion to the left or to the right, right? So the stronger the motion signal, the easier it is, right? And so you move faster and reach the point at which you decide, it's to the right earlier, right? And the other thing is that at the end you make a decision, right? So if you divide the data in terms of a decision, because prefrontal neurons are also, just as I talked about parietal neurons, they're selected to eye movement. You're going to see an effect of the decision, right? So you get to the same point, irrespective of which one. Yes, irrespective. That's fine. We didn't have to go through that. I wanted to make that point clear. Okay, so you get to the same endpoint, very, very much the same endpoint, independent of what the stimulus was. Okay. Now.
So now B.
Okay,
yeah. Okay. So B is in B we just see the same data, but on like we said, it's multidimensional space, and we ignored some dimensions. So now we ignore the motion axis, and we refer to how much the variability is explained by color. So we see this, but only we rotated our like in three-dimensional space. We rotated to a different two-dimensional space. Okay. And
so color shouldn't affect much, right? I mean,
but color shouldn't affect much, but we see that it does, and that means that there is an effect of color on the prefrontal cortex neurons, also when it's the motion context. And this, if you remember our hypothesis, that means that the information is not separated before it reaches the prefrontal cortex, but all the visual stimuli reach the prefrontal cortex, and only then we learn to refer only to what we care about. And you saw that the monkey does make a decision only about the relevant, not only but mostly about by the relevant.
Let's just make the point here. I don't think we'll have time to go through.
Yeah.
Let's just make the point here that this is a motion context. So all you have to tell the dot moving to the left or right. But you do see that the trajectories are very different depending on the color. Okay, so we've seen this at the individual neuron level. Now you see this at the population level here. So although you have sort of what you have to sort of attend to is just motion, color does explain some of the variance, a lot of the variance in the pattern.
So I move on because I don't have any time. Is it clear? Okay. So here we just summarize the graph. The ideal graph will behave like this. Our graph was more noisy. So we will have in the motion context, we're going to have an impact of motion only. The line are black, so we just refer to the motion coherence. So in the color context, we have motion impact on both axes because we said that that's the result we saw. And we said that this means that there isn't a separation of the information before it reaches the prefrontal cortex. And in this side, if there was a separation, motion shouldn't have any impact on the results because there wouldn't be any motion input.
Is that clear, everyone? That's an important point. I mean, is there a selection early so that motion, color information is irrelevant when you're doing a motion judgment, or not? And okay, and the answer is what?
What?
Is there a sort of an early selection or a late selection?
So late selection, because we see that all the information have some impact about the behavior of the neurons, even if not on the decision. So they wanted to make a model that maybe could explain how why the neurons behave the way they do. So they made a neural network which gets an input which refers to the motion coherence, but with a noise which is taken from a normal distribution, and in each point of time, because the dots move, so one dot leaves the screen and another gets in, so it's slightly, there are little changes in the coherence level, but the mean should be the coherence level. And the same about color. And the network also gets input which refer in which context we are, if we are in the motion context or the color context. And after some time, the network should make a decision, should either +1 or -1, and they should reflect the monkey's decision to make a circle towards the right or towards the left. So we have
How do you train a network? What do you do in terms to train a network?
I guess you just show, you just give some parameters and you tell if it did a correct choice.
You have a teacher, right? You have a teacher, and back process
sure.
the weight. I mean, what's important here is really the weight between the neurons here.
Yeah.
That's what's the trick. Yes.
Okay. So this is the result from the model, and we see some of the features were kept, like the fast increase at the beginning, but the decrease at the end, we don't see a decrease of the impact of the motion or the color at the end, but when the stimuli is removed, there is a drop towards the attractors, and we see that the two inputs have effects on the behavior of the neurons. So this is the same like in the behavior of the real prefrontal neurons, and we see here the line attractor and the fixed point. But line attractor, it's just they identified by identifying slow dynamics and identify how much is in standard in which direction vibration from this line gonna lead us. So this is the attractor, and if we reach the attractor in this part, we make choice 1, and in this part we make choice 2. And here we see the same. I actually explained it before. Okay.
Your time is over.
Okay.
Yeah, I think we want to summarize. You don't have time to get into that.
Yeah, I don't.
That's beautiful, but you don't have time.
Okay.
Just give a summary.
So the summary, first we saw a way to explore neural behavior by how much the variability in the responses is explained by the parameters, and we also saw we also offered a dynamical model. We didn't, but we would if we have time. That will explain how the context